the law of conservation, of energy, G. This fundamental law of the universe says this. The total energy of a closed system, and what I mean by a closed system is one where you have not attached a battery or attached a motor, or you have no outside energy sources. There's not something adding energy to the system. So you haven't attached a motor to the system, you haven't attached a battery to the system, you haven't added gasoline or gunpowder or something like that. The total energy of a closed system is neither increased nor decreased in any process. Energy can be transformed from one form to another, but the total energy remains constant. The poetic way of saying this is the amount of energy in the universe after the Big Bang has never changed. We've not created any new energy. We haven't destroyed any old energy. The amount of energy in the universe is constant. Also, according to the work-energy theorem, if you have a closed system, you haven't added a battery, you haven't hooked up a motor, you're not adding gasoline, you're not adding extra energy. If we have a closed system, you get no useful work. So we have the work-energy theorem, work equals change in potential plus change in kinetic. If you don't allow any outside energy sources, you get no useful work, which means the amount of work is zero. Kimia, what's change in anything? So I can write this as 0 equals PE final minus PE initial, potential energy final, minus potential energy initial, plus kinetic energy final minus kinetic energy initial. I could leave the equation like that, and I know some teachers that teach it that way, but I have a minus here and a minus here. I'm going to plus them over to the zero side. This is how I've given you the law of conservation of energy. On your formula sheet, it says this. The amount of kinetic energy that you start with and the amount of potential energy that you start with has to equal the amount of kinetic energy that you finish with and the amount of potential energy that you finish with. The total energy that you start with is the total energy that you finish with. If you start out with 1,000 joules, you finish with 1,000 joules. Now, you might start out with 600 of kinetic and 400 of potential. If you have 300 of kinetic, you better have 700 of potential. Otherwise, there's an outside energy source either siphoning energy off or adding energy to the system. Otherwise, you're violating the law of conservation of energy. Oh, we can also include friction. This is the one that I gave you on your formula sheet. If you want to, you can add to the blue formula sheet. If we include friction, it looks like this. KE initial plus PE initial equals KE final plus PE final. Write that down if you want to. Don't write the next bit down. Supposing I have 500 joules of kinetic and 800 joules of potential. How much energy am I starting with? Do the math in your head. And supposing I end up with 100 joules of kinetic and 900 joules of potential, do my numbers balance out? So this is what you can add. The rest of it must have gone into heat due to friction. I did the heat in red to make it look like, ooh, heat. A terrific example of this is a skateboard half pipe. A terrific example of this is a skateboard half pipe. I'm going to turn friction off, so I've just turned friction to 0. I'm going to give us a little bar graph here. I'm going to lift this skateboarder up. What type of energy did I just give this skateboarder? Gravitational potential. How is that calculated? What equation is this? MGH. Okay. As I let the skateboarder go, What do you notice about the total energy of this closed system? Doesn't change. That's the law of conservation of energy. But you'll notice we're transforming energy from potential to kinetic back to potential. Where will I have the most potential energy? When I have the least kinetic energy. When will I have the least kinetic energy? When I'm stopped. Where will I be stopped at? The top. Why? Because of the law of conservation of energy. We've done it through kinematics and understood that, but here's the reasoning of why. I can't possibly keep going up. I would have extra energy kicking around. I must have come to a stop. All of my energy is potential. At the bottom, how much potential energy will I have? How much kinetic will I have? Total. Where will I be going the fastest then? Which is kind of Captain Obvious. You figure this out when you're 4 or 5 or 6 years old and learning how to ride a bike. You clue in, oh, I'm going to be going fastest. My mistake. 4 or 5 or 12 years old, learning how to ride a bike, however old you were when you learned. We know our audience, right? But you figure out pretty quickly, I go faster when I go downhill. I go slower when I go uphill. Here's why. Oh, and this is why it's more tiring to go uphill, because if you want to keep your speed up, you have to add energy. It's no longer a closed system. Where is the energy coming from? The food that you ate. But do you have to add energy when you're going downhill? Oh, heck no. Now, this is ignoring friction. If there was no friction in a skateboard halfpipe, you could just go back and forth and back and forth. I'm going to turn friction on now. Does the total energy change? No. That's the law of conservation of energy. But you can see there's less left over for potential and kinetic because heat, due to friction, is bleeding that total energy away and turning it into heat. And generally, once it's in that form, we can't get it back. We can't do much with it. So eventually, will I lose energy? No. The law of conservation of energy says you're not going to lose energy. Will I lose useful energy? Yeah, it's all going to get turned into dissipative heat. The other nice thing is because work and energy are scalars, the path that we take doesn't matter. So here's a track. And by toggling this button right here, I can glue the skateboard to the track because I have a feeling in real life he might fly off the ramp. So I'm going to glue the skateboarder to the track. But it doesn't matter the path that I take then. If I give them some potential energy, we're good. Oh, I got friction turned on. Dumb. Let's try that again, Mr. Dueck. If I give him some potential energy, how about that much? I've got friction turned off. With this system, is it ever possible for the skateboarder to touch this red thing here? Why not? That would violate the law of conservation of energy because you'd be getting energy from nothing. Now, in real life, Mr. Dueck, I've watched skateboarders. They do go higher. Yes, they're shifting their center of mass, and by doing that, they are adding energy to the system. That's why skateboarding can actually be exercise. It's tiring. You're adding energy to the system. But the nice thing is, because this is a scalar, it even works if I do that. Or if I do that. Now I realize it's a bit oh, did he fall off? I didn't see how he fell off there. I didn't see what happened.
He just kept going.
Oh, I just moved it. It just kept going, moved it over. Oh, I know what happened. I lowered the whole track, which gave him more potential energy. Okay. Now, some of you are saying, Mr. Dueck, that's so unrealistic. Can you please not have them stick to the track? Okay, so if I put the ramp kind of like that, and if I start them off here, and if I turn off sticking to the track right now, I get this. So that's a very different situation. But my point is, Because work and energy is a scalar, it's ideal for analyzing curves. Okay? We'll let them go. Example 1. A projectile is launched into the air. It reaches a final height of 93 meters. What was its initial velocity? Use energy to solve this. Now, I could, don't write this down, I could go VI equals question mark, A equals negative 9.8, D equals 93, VF at the top equals 0, and I could solve it using kinematics. I think I would use VF squared equals VI squared plus 2AD. But for what it's worth, I can also solve this with energy. I can use kinetic initial plus potential initial equals kinetic final plus potential final. Justin, does this question mention friction or heat at all? So I don't need to go plus heat. And now I always pause and I ask, are any of these 0? Let's look at potential energy. Potential energy, which is mgh, it will be 0 when we're on the ground. Are we ever on the ground?
Yeah.
Where?
The beginning.
PEI, yeah, it's not a real province. We all know that, right? They call themselves a premier. They are mayor. You're not the premier of PEI. You're a mayor. Let's be honest. What about kinetic energy? Are any of those 0? I think at the top for a split second, yes? And so now I can say a half m v initial squared equals m g h final. Mr. Dueck, they didn't tell me the mass. Did they need to? What was that, Ethan? Yes, they do. Ethan, it wants me to find VI. How would I get the VI by itself? How will I move that 1/2 over? I can either divide by 0.5, but you know me enough to know that I prefer to just multiply by 2. So I'll have a 2gh final, that equals VI squared. Last step. Yep. So it's going to be the square root of 2. Mr. Dueck, positive or negative 9.8? It's a scalar, so it's going to be the positive value. 93. What do you get? It's roughly the square root of 2,000. Something in the 40s?
Yeah,
42.7 meters per second. Now, I gotta be honest, I don't know if I would use energy to solve that one. I would probably have solved that with kinematics, because kinematics, the physics 11, VF and VI and A and T and D, I can kind of do that in my sleep, Daniel. Where would I use conservation of energy? The law of conservation of energy really shines if you notice that there is a change in height, a change in speed, and especially if there is a yucky, curvy path. Or when heat and friction are involved. What this really means, though, is if conservation of energy is good to use when you're finding a change in height, a change in speed, and yucky, curvy path, roller coasters, baby, roller coasters. I guarantee you, on your test on this topic, there will be at least one roller coaster question on the written section, probably 2, possibly 3, because I'm nuts about roller coasters. And it's a neat application. Example 2. A roller coaster car is traveling at 22 meters. If the car starts out at a height of 12 meters, how fast will the car be going when it gets to ground level? I'm going to dulp. And my dulp is going to look, I don't know, Kimia, something like this. Mr. Dueck, couldn't it also look like this? Or could it also look like this? Scalar, who cares? All I know is we were here at one point and we ended up there. That's the beauty of conservation of energy, of work and energy in general. They're scalars. And I think I'm going to call this initial and I'm going to call this final. Does that jive with what we're reading? And let's put a little roller coaster car right here. And a little roller coaster car right here. What else do I know? What else should I add to my diagram? Right? Okay. 12 meters. What else should I add to my diagram? VI. Okay. If you can write small and you want to put the 350 kilograms right there, you can. You may have noticed I usually tend not to put my actual masses on the diagrams. I figure I can see the kilograms in the question, whatever. Here's the real question. Grace, my joy, is there a change in height? Is there a change in speed? Is there a yucky curvy path? This is a job for conservation of energy. So I'm going to write KE initial plus PE initial equals KE final plus PE final. Are any of these zeros? Oh, you mean PEI gets to stick around this time? Boy, some money must have traded hands for that bridge. I mean, good for them. I like Prince Edward Island. I'm just trying to think of stupid ways to help you remember this stuff. I'm from PEI, Mr. Dueck. Oh, you're the one. Oh, gee, I did it again. What else is zero? It's one of our provinces, but it's a really, really tiny province. Okay. Like really tiny. And so the joke I always make is it's not a province. They should be called a mayor. It's a city, not a province. But they somehow managed to get a big bridge built out to their island. So a lot of money. Okay. Anything else? Zero? Okay. Well, what's the equation for kinetic energy? A half m, so V initial squared plus, and potential was m g h initial equals a half m V final squared. Gabe, can you see why I wasn't that worried about writing the mass on the car? What? Have you gone on a roller coaster before? Have you gone on a roller coaster before? Before you got on the roller coaster, did they make you step on a scale and weigh yourself? Did they carefully spread out heavy people and light people? Did they have to make sure very safely that we evened out all the masses? Did they have to do that before you went on the roller coaster? No? Really? Do you know why? But shouldn't you have wondered why they didn't do that when you got on the roller coaster in the first place? Or were you just blindly trusting the engineers? We don't have to step on a scale before we go. In fact, an empty car on a roller coaster will make it all the way through the coaster the same way as a full car will. What am I trying to find? VF? How to get the VF by itself? I could divide by 0.5 and then square root. I'm a math nerd and I always like elegant solutions. So what I'm going to do instead is go times by 2, times by 2, times by 2. Grace, did I multiply everything by 2? That's legal then. If I didn't multiply this middle term by 2, that would be illegal, but times 2, times 2, times 2. The reason I did that is 2 times a half is 1, 2 times a half is 1. Those all cancel. It clears all my fractions, and I get this. Vi squared plus 2ghi equals Vf squared. Before I square root, Ben, don't write this down. I'm just going to write something underneath it. Vi squared plus 2ad equals, I'm going to write Vf squared equals Vi squared plus 2ad. Can you see this is, we've actually derived that equation because g is in meters per second squared and h is in meters. At the beginning of the year, I derived this equation with you, but to be honest, the best way to get this equation is to realize, oh, it's conservation of energy rewritten. Pops right out. That's also why, because technically this is a scalar equation, that's why you have to sometimes, when you square root, add the negatives after the fact, because it's not designed to give you directions. It's really not. It will sometimes, but it's really not meant to. Anyways, Ben is dying to say how to get rid of a squared. Okay. (22 squared plus 2). Now, there's a bit of a built-in error check. Gabe, you said you'd been on a roller coaster before? I know my speed at the bottom is faster. I know the answer better be bigger than 22, or I've messed up. Or I want my money back on that roller coaster. I mean, that's the other possibility, I guess. That's a lame roller coaster, possibly. What do you get? (26.8 meters per second). Is that fast before you turn the page? Yeah. Let's convert that to kilometers per hour. How would I convert that to kilometers per hour? Oh, times by 3.6, what do you get? 96. That's not bad. I've been on a few faster, but you know what? 100 kilometers per hour in a roller coaster, I'll pay for that. I'll do that. Yeah, that's not bad at all. I've been faster at Six Flags, but that's pretty good. Now turn the page. An 18-kilogram object is dropped from a height of 40 meters, and it strikes the ground with a speed of 25 meters per second. How much heat energy was produced during the fall? Is there a change in height in this question? Is there a change in speed in this question? Is there a yucky, curvy path? No. But is the question talking about heat and energy? Well, then this is a job for conservation of energy. So I'm going to start out by going KE initial plus PE initial equals KE final plus PE final. And this time, since it's talking about heat, I'll mention heat. So this version I did not put on your yellow formula sheet. I figured that's fair game to expect you to realize, oh, we're including heat. That's where the extra energy went. I'll tack that on to the end. For any of these, 0. Oh, we end up on the ground, do we? I mean, PEI gets to have its day in the sun again? Good for it. Oh, dropped means my initial is 0? Because when you let it go, it for a split second, it hasn't started falling yet. And this brings us to one of my most aggravating, silly mistakes that students make. How would I get the heat by itself? Hannah, what? So you're one of my stronger classes mathematically. In my other block this morning, I had a couple of kids say, oh, divide, Mr. Dueck. What's the KE doing to the heat? It's adding. But for some reason, just the way this is written, I've lost track of how many times I've had kids say, oh, it's potential energy divided by kinetic energy. That's not how you get the heat by itself. And that, I'm going to say, that's a sloppy mistake because that's a math 8. Oops. So Try not to do that one. Right? Right. You didn't say divide? Oh, I thought I heard divide from somewhere over here. No? Oh, they would go PE over KE. On a real bad day, they'd cancel out the E's, and then I'd really glare at them. And here's really what we're saying. Here's all the energy you started with. You lost some energy to kinetic. Whatever's left over must have been turned into heat. I'll go red now because heat. It's going to be mgh initial minus a half mv final squared. Oh, hey, Mr. Dueck, the m cancels here too, right? Or does it? Where is there not an m inside of heat? So I fibbed a bit, by the way. We're going to look at roller coasters in more detail because why not? If there's friction, which in real life there is, the m's don't quite cancel. But if you grease the roller coaster up pretty good and you get friction, Danielle, to as close to zero as you can, the masses almost cancel. Now, there's one exception to that, and I don't yet know why. P&E used to have a wild mouse roller coaster. Have any of you been on that when you were younger? They haven't had it for a few years. Disneyland has one called Goofy's Sky School. It's in California Adventure. Okay, they're scary because you always feel like you're going over the end. But the reason I remember the P&E, the Playland ones so much is because they had sandbags in them. So something about that, the M's must not have been canceling. And I wonder how they found that out. Those are the two questions. Because I remember clearly, Ethan, first time I went on that, I was about 12 years old, I think, and I got into the roller coaster. I didn't like coasters when I was a kid. I went on my first coaster at Expo 86 when I was 16, and I remember thinking, I'm nuts. What have I been missing all my life? I'm going on these forever, and I got hooked. But I would go on the Wild Mouse when I was 12 or 13, and I still clearly remember, because I had to sit in the front because I was going with my older brother, having to dodge these sandbags that were in there. And I still, to this day, want to know, why did you have to increase the mass? And how did you find out you had to increase the mass? That's just an aside, and I still don't have an answer for that. But the ones that in California Adventure for Goofy Sky School, because they got more money, I'm sure those are permanently mounted to the track so that they can't come off. The Wild Mouse ones weren't. They were just sitting on top. So, anyways. Well, you can't spell projectile without part of a child, right? You need an I and an L in both. Alrighty. 18 times 9.8. Minus 0.5 times 18 times 25 squared. This might actually work out evenly. What'd you get? So I'll go 1430. I'll go to 3 sig figs. Okay. I like example 4. I like example 4. I like example 4. Example 4 is a nice question. Example 4 really has 3 questions. So let's call this part A, and then part B, and then part C. What's A asking me to find? Oh, work. So this is not the law of conservation of energy. It's work. So, okay. Kimia, the first thing I thought was to go force times distance. Don't write that down. Look at the question. Do you see a force in newtons? Do you see a distance in meters? Oh, my next thought was work is also the area underneath the force versus distance graph. Did they give me a graph? No. Kimia, which version of work am I going to use here? Are any of these 0? I'm looking at this question. I don't see any kind of a hint about a hill. So I'm going to gamble and say, yeah, I don't think so. What's changing anything? What's the equation for kinetic energy? It's on your sheet. I mean, you might have it memorized. You'll probably have it memorized by the end of this unit, but I'm going to do both of those in one line. So I'm going to go work equals a half m final squared minus a half m initial. There's my final minus initial. Okay. 0.5, 1200. Kimia, what's V final? $50 what? Do we do physics with kilometers per hour? How do I go from kilometers per hour to meters per second? It was something to do with a 3.6. Sorry? Divide by 3.6. I'm so lazy, Kimia, if it's okay with you, I'm going to go 50 over 3.6 squared, and I'll do it all in one step. I mean, I could do it somewhere off in the margin, but then how many sig figs do I need to carry? Ah, forget it. I'll do it all in one step. Minus 0.5, 1200, 80 divided by 3.6 all squared. What do you get? Oh, you're going to get a negative answer. Wait a minute, you should get a negative answer because we're not only figuring out how much work, really what we're saying is how much energy does this car need to lose? And losing energy should be negative. Chloe, what'd you get? I think it's way bigger than that. And here's how I know, okay? If I got hit by this car and made it stop, made it go from 80 to 50, I don't think I'd survive. And if I recall yesterday, carrying somebody up a flight of stairs was only about 2,000. Isn't it more than that? What's the answer? Is it 4,000? It's more than that, isn't it? Sorry? I think aren't you going to get something in the negative 100,000s? Yeah. Because 4,000 joules, my body could absorb that. I'd break a bone, but I'd be okay. In fact, I might even break a bone. That's like piggybacking somebody up 2 flights of stairs. It's about the same amount of work. I'm not going into cardiac arrest doing that. So, sorry, but just that number alone, I was going, wait a minute. I can absorb that much, and there's no way I'd want to be on the receiving end of this one. It's got to be something. What'd you get?
Negative 100, negative 1,500.
Is it negative 181? Yes? Okay. And I'll go to 3 sig figs, but blah, blah, blah. Why negative? There's 2 ways to think about it. One way is to realize the car is going forwards and the force is going backwards. So if we did have a force and a distance, we would say they're in opposite directions, negative. Or the other way to think about it is this car has to lose that energy. If it doesn't lose that energy, it can't come to a stop. That brings us to B. What force does the work? Where do you think the energy was transformed to? Now, that's only for older cars. That is not, B and C are not correct for hybrids and most electric cars. So most hybrids and electric cars, they have a very clever circuit so that when you take your foot off the gas, although they often call it the go pedal because they don't have gas, when you take your foot off of the go pedal, you'll feel like you're stepping on the brakes even though you're not. What they're really doing is they're bleeding the kinetic energy off through a regenerative braking system, and they're turning it into electrical energy and recharging the batteries. And since the car is losing energy, it must slow down. Not a friction force that's slowing it down, but it will slow down. This heat is a huge waste of energy. There's a reason why all of the taxi companies switch to Priuses. You may have noticed you don't see a taxi that isn't a hybrid. And the reason is every time they're stepping on the brakes, they're recharging their batteries and they're saving money. Every time a standard car steps on the brakes, you're throwing away that heat. Waste of energy. Internal combustion engines are terribly inefficient. Do they also just give off heat by running? What a waste of energy. Can you hear them from a long distance away? What a waste of energy. When your engine is on, can you actually feel the entire car shaking? What a waste of energy, because you have none of those with an electric motor. I took a Tesla for a test drive about 4 years ago, and oh, very nice. Example 5. An object is pushed across a level floor with the coefficient of friction of 0.35 for a distance of 6.4 meters by an applied force of 58 newtons. Cool. Lorenzo, what does A want me to find? More specific. Oh, so I'm going to argue that A wants me to find work applied. And so my first thought, Lorenzo, would be, this is what I would, don't write this down, I'll just think this in my head. I would say maybe it's F applied times distance. Did they give me an F applied in newtons?
Yes.
Did they give me a distance in meters?
Yes.
Oh, then I will write that down. Otherwise, I'd go looking for a graph. No graph, I'd be going change in potential plus change in kinetic. What's the applied force, Lorenzo? What's the distance? How many joules of work?
371.
Give it to me to 4 sig figs. Yeah. Normally I'd go 3, but I'm going to be doing something with this, so there's the full shebang. So instead of an applied force, Lorenzo, let's make it you pushing one of those gym benches. Okay? So where is that energy coming from? You, the food that you ate. So you have lost 371.2 joules of energy. You're a little bit more tired. But not because work is tiredness, because you've burned up some of the food energy. But not all of that went into making the bench speed up. What's B asking me to find? I guess the work done by friction is going to be the force of friction times distance. Friction is what times what? I don't know the number. Oh, you know what? I should do a free body diagram. I've got room right here. Here's my free body diagram. What are the forces acting on this bench? Get the obvious one. What else? Before that, go systematically. Is it sinking into the ground? Really? Is it sinking into the ground like quicksand? Is it flying like Superman? And I think here, wonderfully, the normal force is equal to mg, like Physics 11 was all the time. I agree there's an F app. And friction. Okay. Mu times the normal force. I don't know the normal force. Oh, but look. I don't know the force the same size as the normal force. Which one? More specific. Thank you. So I'm going to go mu mg d, which is what? 274.4 joules. Why must this be wrong? Because it is wrong. Why must this be wrong? Oh, because the angle theta between them is 180 degrees. So if you use force times distance cos theta, you'll find cosine of 180 is -1. Or you can just say the force and the distance are in the opposite direction. Or you can say I'm losing that much energy to friction. Heat, as a matter of fact. Ben, what does C want me to find? So the network is going to be the total that Lorenzo was putting in, take away what we lost to friction. Now, what you don't want to do here is a minus. So you can either say the network plus the negative, or you can just say, here's what I started with, here's what I lost, And I'll put a negative there to show that I lost it. Something in the 90s. 96.8? That's the energy, Lorenzo, that went into the bench. Did the bench raise up off the ground into the air? No. So it must have gone into kinetic. The bench is speeding up. Has to be speeding up. Which leads us to the next logical question. How fast? D. Assuming the object started from rest, what's the final speed? Lorenzo, what do we find in part C? Work, you say. Is there an equation that has work and speed in it? What? That's energy, not work. It does not say anywhere on your sheet W equals a half mv squared. So let's try that again. Is there an equation that maybe has a W in it that also has a speed in it? What? The work energy theorem? Could you just read me the equation and then we'll just recover from there? No. Start on the left-hand side. What equals? Thank you. Boy. Felt like I was running a dunking play for you or something. Just futile. Okay. Oh, are any of these zero? Did it say level ground? Ah. Ha-ha. Oh, and it started from rest. So what's my initial kinetic energy? So I can say a half mv final squared. Oh, what am I going to put for work? Yeah, not the 371 point whatever. That's how much work he did, but not all of that went into causing the bench to speed up. Lorenzo, how would I get the V by itself? Multiply by 2 or divide by 0.5. I don't care which. I prefer multiplying by 2. And I think the final step would be a square root. Yes? How fast? Hopefully our numbers make sense. By the way, Chloe, do you see where you zigged on your 4,000? Oh, I'm going to guess missing squareds. By far the most common mistake is kids miss the squareds. I was just thinking I should set up a permanent lifelong auto emailer, and anytime a kid misses the squareds, I would just add them to that email out list, and every 2 months or so they would just receive a random email from Mr. Dueck, and all it would say in the subject line is squared. That would be great, because some of my top kids have lost their only mark of the year by missing a squared. And that'd be a great way to press my thumb on the emotional bruise. And, oh, that'd be good. What'd you get? 1.25? Anybody else? That doesn't sound familiar to me, but maybe it is. 3.94? 3.94? Well, I was going to, but thank you, Captain Obvious. Okay. 3.94 meters per second. We could have done this without energy. We could have done this using kinematics. Don't write this down. I'm just going to walk you through it. We would have said VF equals question mark. We would have said VI is 0. We would have said D equals 6.4. We probably would have said, oh, I need A. How do I find A? This is a job for a free body diagram. Who's winning? F applied. Who's losing? Friction. Equals what? MA. We could find A, and we could find VF. And we would get exactly the same answer, which confirms that the physics that we're doing works. But one of the nice things about the energy method is if there was a curvy, yucky path, this would still work. This method would not. This method would be really ugly. I could make it work, but I need to come up with a calculus expression for a constantly changing angle. Ugh. Why bother? Example 6. Turn the page. I'd like you to imagine that we launch 3 projectiles, but we're going to launch them on the moon. Why on the moon? So I can ignore air resistance. So 3 projectiles, A, B, and C, are fired from the same machine on the moon with the same initial velocity. Their paths are labeled A, B, and C. At the 3 points marked location 1, there, and there, which projectile will have the greatest kinetic energy? Once again, we get to vote. Once again, how high you hold your hand up is how sure you are of the answer. Which projectile will have the greatest kinetic energy at location 1? A, B, C, or all 3 will be equal? Who says location A, Mr. Dueck? Location A. No one. Who says location B, Mr. Dueck? Who says location C, Mr. Dueck? Who says location all 3 are equal? Interesting. My previous block, they almost all voted for all 3 are equal. Convince me. Yeah. What are you defending or attacking? Convince me.
The y velocity at the top are all together. Then the x velocity and c has the highest velocity.
We can do that with scalars and without components. I like your explanation, but I just think it's overcomplicated. My brain thinks that way with algebra and stuff, but not everyone's brain thinks that way with algebra and stuff. So we might need an explanation that's just a little bit simpler so that all of us can wrap our brain around it. Okay? So we'll just... Has he looked up yet? Yeah, oh, okay. Because it was there for a while. I was wondering if he's going to... Okay, we're good. Did they all start out with the same energy? What was their initial potential energy? Meant to be stupidly obvious. 0. And they all started out with the same velocity, same kinetic energy. So they all start out with the same total energy. In other words, they all start out with that thing, the same. When does this object, this skateboarder, have the largest kinetic energy? When it has the smallest potential energy. Right? We've only used up, I'll make up some numbers. Let's suppose we have 4,000 joules of energy to play with. If we've only used up 1,000 joules of potential, then we have 3,000 joules of kinetic. Here, we've used up 1,500 joules of potential. Now we only have 2,500. Now here, we've used up 3,800 joules of potential. You only have 200 joules of kinetic. Is that okay? So, what does law of of E stand for? Law of conservation of energy says that less PE means more KE. Is that a good enough explanation without doing a long paragraph? So now, part B, same situation, but instead of the greatest kinetic energy, the greatest total energy. Once again, we're going to vote. Who says A, Mr. Dueck? A. Who says B, Mr. Dueck? Who says C, Mr. Dueck? Who says D, Mr. Dueck? Convince me. Ethan.
Like the mouse is on.
Yeah. Does that change at all during the flight? So did they all start out with the same potential? Did they all start out on the ground? Let's look at the picture. Did they all start out on the ground? Yeah. And it says they all started with the same velocity, which means they all had the same half mv squared. So did they all start out with the same initial amount of energy? they'll have the same energy throughout. Each one of them, if they have 3,000 joules, they'll have 3,000 joules of total energy throughout. And what's happening for all of them is the kinetic is being turned into potential, so they're all slowing down. Some of them, the kinetic is being turned into potential really fast, situation A. Some of them, the kinetic is being turned into potential slower, situation C. Have I convinced you, Justin? That's what we mean when we say energy is conserved. The amount you start with is the amount you finish with. What about at location 2? Here's location 2. Which one will have the greatest total energy? What's the correct answer? I'm not going to vote. What's the correct answer? All of them, because the total energy doesn't change. Oh, you know what? Copy, paste, copy, paste, because it really is the same question. For now, if you're wanting to try some questions, I got a little further with my block A's. Here's some of the questions that I gave them to try. Number 1. Now, if you look at number 1, don't overcomplicate it. ME is potential plus kinetic. It's mechanical energy. So what I did is I went to we went to half mv squared, and we filled in that there was 1,920 joules. You can fill that in right now. And I just went 0.5 times 60 times 8 squared. How high is the skateboarder at location 1? How high is the skateboarder at location 1? So how much potential energy do they have? So I filled in that 0, and I said, oh, okay, I'm starting with 1,920 joules of energy. How much energy must I have everywhere? 1,920 joules of energy. From this height, you can figure out how much potential, how much is left for kinetic, how fast they must be traveling. Here, the fact that V is 0, oh, you can probably fill in the kinetic energy right now. How much kinetic energy do they have right there? You can figure out how high they must be. Okay, so number 1. Number 2, very similar to number 1, roller coasters. 3 is good. 4 is good. 7 is good. 9 is good. 11 is good. 12 is good. 13 and 14. That's a lot. I'll try and I know I have a couple of lessons from now with no homework, but I want to see if we can get the test in before Christmas, so I don't want to take my foot off the gas pedal.